Okay, everybody, I know that there are much better ways to show a very, very short video lecture than to point a video camera at a computer monitor. But I want to also point it down at my page and do some work with you on paper, and the fastest way to do this right now is to just point the camera at the monitor and talk you through it, because this is only going to take about 1 minute. Our next topic is gravitational field. And that's a little different than universal gravitation, because universal gravitation is a force. So imagine out in space, you can see the Earth hovering here in the blackness and the emptiness of outer space. Now this is a mass, and Einstein tells us that space isn't what we think it is. It's not just an emptiness. There's a fabric to space. And if you take anything that has mass and place it in that fabric, it's going to warp the fabric. So the fact that Earth has mass means that Earth warps the space around it. Now this is a very difficult thing to show on a picture, because space is not two-dimensional like a sheet. So it's not like the Earth is warping space in a downward well like this. It would be warping space in a three-dimensional sort of configuration, which is very difficult to try and show. But anyway, this warping of space is independent of whether there's anything else there. It's just the Earth, and it's just the mass of the Earth itself. Okay, it's not until, well, I'm sorry, that is what is called G. So that is gravitational field. It's not a force, it's the bending of space that results in the mass of Earth interacting with the fabric. And it's not until something else wanders into that space, for example, the moon, where it will feel that curvature of space, and it won't actually attract to the Earth. See, that was always a very presumptuous sort of thing for ancient astronomers and physicists, is this idea that masses attract one another. It's not really that masses attract one another, it's that Earth bends space, and the moon, being another mass in the vicinity of this bend, feels the curvature of space and actually starts to almost think of it as rolling into it. Then there's a force of attraction. Then we have a gravitational force. But we want to take this back a step and look at the field itself. And this gravitational field is what's responsible for, you could argue, all life on this planet is because of the gravitational field at the surface of the planet. Don't forget, life on Earth probably started off as just microbial life that really had no sort of complex organization to it. And as life evolved, there was one constant at the surface of the Earth that really didn't vary, and that was the gravitational field at the surface of the Earth was here. And there was a gravitational force downwards. And that's responsible for so many things if you think about it. Like, for example, our entire digestive tract, the fact that it starts off at the top and ends down lower, that's a direct result of the fact that gravitation is attracting things downwards. Think of your nose. There's a reason why it's angled that way and that your nostrils face down. It's not just random. Things fall. Things are attracted to the surface of the Earth. And so to keep these particles out of your nose faces down. Your eyelashes, the same type of idea. Your eyelashes are bigger on top than they are on the bottom, because most instances, masses are going to be falling from above, and you don't want to get those in your eye. When we planned a mission to Mars in 2020, and COVID did not interrupt this. We had a launch of the Mars 2020 rover in, it was either July or August of 2020. It's in the air right now, It's in space right now, and it will be landing in February of 2021. So there's something that we can look forward to. It's an unmanned mission, of course. It's robotic. But in order to go to another mass somewhere in space and be able to land on the surface, we have to have an understanding of how to calculate gravitational field. See, the gravitational field of Earth right now is 9.8. And you can test that because it's an acceleration. If you drop something right in front of you right now, it will accelerate downwards at 9.8 meters per second, faster per second. But we're not going to go to Mars and drop something and see what the acceleration of it is, and then come back to Earth and say, okay, now we know what the gravitational field of Mars is, let's build something and get it there. Same with just this, the International Space Station. At this distance above the surface of the Earth, we need to have some way of calculating what the gravitational field will be this far away from the planet, because it's not the same as the gravitational field here at the surface. Not the same as force of gravity, but the gravitational field. Okay, so if I can go down to the paper now, and hopefully you've already printed this off. If you haven't, pause the video right now. We're going to switch to this paper that has the title at the top saying gravitational field, and we're just going to do a very quick derivation and one quick example, and then I'm going to refer you to the textbook. I had the lights off so there was no reflection in the video. Let me get up and run and turn the lights on. So let's do a quick derivation for how we can come up with a formula for lowercase g. That's what gravitational field is, lowercase g. The same lowercase g that you've been using all through grade 11. But how do we get it? How do we get a formula for it? And there's one easy derivation, and see if you can understand this. There are two ways that you can calculate your force of gravity right now. Okay, your force of gravity. You could do it the easiest way possible and say that your force of gravity is, if you take your mass, the mass of u, and you multiply by g, you would get your force of gravity. There's another way you could get your force of gravity. You could say, well, I don't know 9.8 or what lowercase g is. I could think of myself as an attraction between this giant mass called the Earth and this little tiny mass that is you, and the distance between them. So this is universal gravitation. So you could do the same calculation using universal gravitation and you'd get exactly the same force. So you would have to take capital G, the universal constant. You would need to multiply by the mass of the Earth. You'd have to multiply by the mass of u, and you would have to divide by the distance between the center of the Earth and you, which is, that distance, you might as well call it the radius of the Earth. Your height, or the distance from the center of your body to the outside of your body, is really irrelevant here. So this would be the radius of Earth squared. That would be your distance. Well, if you look at what's on the page here, your mass occurs here in the formula and right here in the formula. And both of these formulas give you the exact same result. So wouldn't it also make sense that everything else in this formula, and there's only one thing, g, and everything else in this formula would also be equal? Well, that's it. The easiest derivation you can possibly go through. But a formula for g, if we take exactly what's written here and write it just in a more general sense, g equals, lowercase g, gravitational field equals, taking the universal gravitation constant, multiplying by the mass of whatever the object is that is warping space, and dividing by the if it's a spherical object, and all of our objects will be, dividing by the radius. And not necessarily just the radius of the object, but the radius as far out from the object as you want to go. So for example, what I mean is, I'll scribble off here to the side, if you have Earth and you want to calculate the International Space Station hovering above the Earth this far, rotating above the Earth in orbit, you want this. You want to use the distance from the center of the Earth up to the International Space Station's orbital altitude. That would also be the radius of a circle. So here's your formula. You multiply by the universal constant, the mass of the object, and the radius from the center of the object out to as far as you want to go. We're going to do one quick example here, And then on the back side of this sheet, you're going to follow a sample problem from the book, and you're going to do a couple of practice questions. This question says, what is the gravitation, sorry, I missed some letters here. It should have said gravitational field. What is the gravitational field strength in the chair that you are sitting in right now? Well, let's do that calculation. G equals capital G multiplied by the mass of the object that's warping space. So not your body, but what's causing the gravitational field. And divide by the radial distance from the center of that object out to where you are. And that has to be squared. So G is 6.67 times 10 to the negative 11. That's the universal constant. The mass of the object that's warping space and causing the field that you're feeling right now is planet Earth. And the mass of Earth, I'll save you the hassle of looking it up, 5.98 times 10 to the 24 kilograms. How did we get such a ridiculously exact value? Well, actually, it was the ancient Greeks that did that, so it didn't even require today's technology. And finally, you need to divide by the distance where you want to check and see what the field is. So right now we want to check the field right where you're sitting. So basically it's at the surface of the Earth. It's not higher up in the air. So we're going to use the radius of the planet, and I'm not sure if you know what that is. It varies at several different instances around the Earth. It's 6,370 kilometers. So I'm going to have to tack on 3 extra zeros to make it meters. So 6,370,000 meters, and that's going to be squared. So take out a calculator, try that calculation, and I'm going to do it off to the side here. And you really should try this calculation because of the scientific notation. Among other things, I want to make sure that you're doing scientific notation right. For some of you, it's been a while. So do that calculation, and you get 9.8. You actually get 9.83 meters per second squared. But basically 9.8. So that shouldn't be a surprise. But there's sort of a disconnect because we use 9.8 all through grade 11 as acceleration at the surface of the Earth. And it is the acceleration at the surface of the Earth. But it's the gravitational field. So rather than just stating that acceleration is always 9.8, you want to have a way of calculating gravitational field so that now you can look at anything. It doesn't have to be the Earth. You can look and see what the gravitational field is at the surface of the moon or on the surface of the sun. Or you could look and see what the gravitational field of Earth is, not at the surface, but what if you go up another 300 and something kilometers to the International Space Station? One of the homework questions gets you to do that. And see what the gravitational field is if you were an astronaut on that, on the ISS. So please flip the page, and there's another example that I want you to write out, but it's right from the book. Go through that example, and then there are 4 homework questions, I think, if I'm not mistaken. Each one of them was slightly different, so there wasn't any one of those questions that I could take off and say ignore because this is just copycat work. So please do all the questions, and as usual, the full solutions will be posted shortly.